go. We are recording. Um, First of all, I'm audible. Yes.
Yeah.
Perfect. All right. Quick course logistics things. The problem set is due by tonight. Problem set 4. The late day for problem set 3 is also tonight. Um, the programming assignment is due on Monday. I will hopefully release problem set 5 later today. It's going to cover hashing things, which we started talking about yesterday and we'll continue talking about today. Um, that's everything that's due. Uh, as a reminder, please refrain from discussing the exam until at least after Monday, when hopefully everyone should have taken it. Um, and you can hopefully expect exam grades sometime next week. Um, yeah, that's all I got on the logistics front. Does anyone, are there any questions? Any uh any concerns that I can address before we start content? Cool. All right. Well, let's get into content then. Oh, I posted the whiteboard from yesterday's lecture to Brightspace. Um, did people look at that? Did that show up all right? Was that helpful? Should I continue doing that? Okay. So yesterday we talked about um, hash tables, right? To continue if it's not a huge burden. Yeah, for sure. It just requires me to be more coherent with how I lay my notes out, but that's probably good anyway. So, um, okay. So last time we talked about hash tables, right? Which is like an array of values indexed by a hash function which we called h, goes from a set of keys to the range 0 to m, where m is the size of the table. Um, we talked about uh, collisions, right? How collisions are bad. Because in particular, anytime the size of the key space is greater than n, the size of the table, uh, greater than n plus 1 because it's 0 indexed, um, there are always be at least 2 keys that map to the same index, right? Um, this is, of course, bad because if we think about our um, example from last time or from last class, right? We had an array of numbers and we wanted to figure out which, we had an unsorted array of numbers and we wanted to find which number was repeated in this array. So we had like 1, 3, 2, 3, 5, 6 maybe, right? Um, And let's say my table, let's say m equals 2, right? And my hash function is just k mod 2, right? So I've got a table with two slots in it, one that corresponds to 0, one that corresponds to 1. I look at 1, I insert it here. I look at 3, I go to insert it here, but oh no, there's already something in this position, right? So I mark this as repeated. Okay, this was bad. Let me replace this with a 5. Pretend that's a 5, right? 3 was actually the answer. But if this is a 5, it hashes to the same place that the 1 hashed to. And now I think I found a collision because, or I think I found the duplicated element because, hang on, one moment. There we go. Okay, the 5 and the 1 hash to the same spot. So I think I found a duplicated element when in reality I haven't. It's just they happen to hash to the same spot, right? This is bad. Um, and of course, if uh, I don't know, maybe I actually store the value here and I go, oh, okay, 5, so that's different. But now if I replace this 2 with a 7, I really should have crafted my input more carefully. But okay, so I have the 1 here. I replace it with a 5. I say, okay, I found a 5. I find a 3, so I replace it here, right? I find a 7, so I replace it here. And now when I find the second 3, I forgot that I had a 3 here, right? So the fact that multiple keys can hash to the same space is, in general, this is not something we want because one key might overwrite the other, or the second key might never be inserted or whatever. And so our algorithm will be incorrect if it relies on keys being in unique positions. And if the algorithm doesn't rely on keys being in unique positions, then we're not really like taking advantage of the fact that we have a hash table. And so um, the moral of that story is that collisions are bad. And what I hope to talk about today is ways to deal with collisions and ways to design hash functions. So how do we come up with this? And how do we deal with what happens when age of key one equals age of key two, or key one not equal to key two? Okay. Does what we've talked about for hash tables so far make sense to people? Like the mechanics of how it works, the idea that we have something where we want constant time insertion and lookup. Makes sense? Cool. All right. So let's start by talking about common classes of hash functions. So the first thing that I think we talked about yesterday, or I think maybe I mentioned yesterday, is the fact that all of our hash functions sort of assume that the output is going to be some kind of non-negative integer, right? Or positive integer, because we're using this to index into an array. Of course, the keys that we have might not be numbers, right? Where we can apply some like mathematical function to them, right? Like PUIDs, you can think of as numbers, or you can think of them as strings of 10 characters or something like that. You might have you might want to hash a binary tree, for example. That's very clearly not an integer. Um, so the first step to any hash function is to convert the key into I'll just say a natural number. Right? Different ways of doing this. If the key is already a number, if the key is already something numeric, then you can just treat it as a number. If the key is like a string, then you can look at like ASCII codes, right? And then think of it as a base 256 number, or maybe base 128 if you know that your string is going to be like printable characters or something like that. Um, if you've got something like uh, a binary tree, or if you've got, yeah, so if you've got something like a binary tree, um, you can use some kind of like combination function, right? So if I've got something like this, I can sort of recursively, I can say the hash of this tree is some function applied to um, the hash of the left subtree, the hash of the right subtree, and the hash of the root, like the hash of the root value, right? Um, and this can be whatever. Like if I assume that I get something numeric out of these three, then this function can be, maybe 2 to the x, 3 to the y, 5 to the z, right? Whatever, it doesn't really matter. Um, or it can just be like x plus y plus z, right? Just some way of combining these three. And so I can sort of recursively build up a hash of a binary tree. I can do this for a graph as well, right? Um, in general, you sort of have creative freedom for how you want to hash a data structure or how you want to hash something like this, right? If you've got a struct with maybe some like uh, uh, some type T and some type S, right? Maybe you compute the hash of X, you compute the hash of Y, and then you concatenate these together or something, or you like add them together or something, right? So like the hash of this thing is just a hash of X plus the hash of Y. I don't know, right? So the point is, for the remainder of the time that we talk about hash functions, we're going to assume that the keys are somehow expressible as numbers, as natural numbers. And if they're not, then you sort of figure out a way to do it. If it's a negative number, maybe you take the absolute value, right? If it's a floating point, maybe you uh, do some like bit hacking to think of it as a 32-bit integer. I don't know, right? You sort of find some way of expressing the thing as a natural number, and then the 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 interesting thing that we're going to look at is how do we map an arbitrary natural number into the range 0 to m of our table, right? Um, and so in particular, for this part, we're going to look at two different techniques. We're going to look at division and multiplication, right? There's other things that you can use, but a lot of times there'll just be some sort of composition of these two, right? Um, so this turns out to be pretty straightforward, actually. Uh, division is the hash of a key is just k mod m, right? This is very easy because, I mean, this is very efficient, right? It requires a single division operation, and then we just look at the remainder, right? Um, for example, and of course, this like nicely guarantees that everything is going to live in the range of our table. The other one I'll talk about is multiplication. For this, we need to pick some constant, which I'll call capital A. What you do is you multiply k times capital A. You look at the fractional part of that, and then you multiply that by m, and then round down, right? So mod 1 is like 1.3 mod 1 equals 0.3, right? That's the idea. Here, you sort of pick the constant A. The hash function depends on the choice of A. There's, if you know something about the distribution of keys that you're going to care about, then you might like pick a in a particular way. Um, According to the textbook, there's a paper by Donald Knuth, this guy, um, which claims that setting a equal to roughly the square root of 5 - 1/2 is good. I don't really know why this is good. If you care, maybe read the paper. Um, but a lot like in practice, what you'll do is you'll find some like approximation which is close to this irrational number, and then implement it that way, right? Multiplication or hashing via multiplication turns out to be um, efficient if you're careful about what m looks like and what a looks like, right? So, for example, for a, um, we can set it to be some sort of localize away from 2 to the 32, right? So we can set it to be something like uh, s out of 2 to the 32, uh, where s is chosen such that this is close to this ideal value of square root of 5 - 1/2, right? But we just make sure that it's some like multiple of 1/2 to the 32. Um, and then we set m to be a power of 2, right? So this part means that if all I care about is the fractional part, I can just do k times s, right? Um, and then I get some like looks like a d. I don't want, yeah. I can do k times s. This is going to be something over 2 to the 32. So this is going to be some like 32-bit some sequence of 32-bit words. If m is a power of 2, then I can just chop off everything that's above whatever power of 2 that is, and I can just look at like the bottom few bits or whatever. And so I can do some like bit manipulation to get away with computing this with a single multiply, right? So maybe I want to say efficient with a single multiply when a is s over 2 to the 32 and m equals 2 to the p, right? So in general, if I'm careful about choosing the size of my table or the sort of hashing algorithm I use or whatever, I can make sure that hashing is pretty efficient. Question I had last time: what is an acceptable allocation for hash maps? Where do we start caring that our current hash is too big? Like when do you start caring that your current hash table is too big? It depends, I guess. You so the thing that we're going to talk about is this like load factor, right? Um, which has to do with like how many keys you expect your hash map to contain. Um, you want your hash map to not be too much bigger than the number of keys it is going to contain, right? So if you've got a million keys, for example, the um, if the domain you're working in means that you expect to have a million keys, then there's not really you can't really do much better than having a hash map with a million entries, right? Or something on the order of a million entries. Um, but if you're only going to have like 10 keys, then there's no point in creating a hash map that big, right? It also matters like if you're uh, like severely memory constrained. If this is like a hash map on like an embedded device or something like that, then you might have like a physical constraint of like I can't afford to allocate more than like a few megabytes or something like that. Um, but yeah, I guess the question is very broadly, it depends. Or I guess the answer is it depends. Does that does that answer what you were asking? Or did I misunderstand what you were asking? It does. Okay, cool. Um, so yeah, we've got uh two classes of hash functions, one with division, where we just mod by m, and one with multiplication, where we sort of do this complicated thing. We multiply by some fraction, Maybe I should say like 0 is less than a is less than 1. Um, we multiply some fixed a times our key, and then look at the fractional part, and this gives us some like ratio of how far along M we're going to look at. Right. Um, this is also like multiplication or hashing via multiplication is good in the sense that if the key has like it's very good at like destroying patterns that show up in the keys, right? So for example, if the M we choose for division is something something easy like a power of 2, right? So if M is like 16, for example, right? Then K mod M is just going to look at the lower 4 bits of the key, right? Which means we're going to have a ton of collisions unless we expect the lower 4 bits of the key to hold a lot of information, right? So for something like this, in general, you're going to want M to be prime, right? That's just going to sort of make it more likely that all of the bits of the key are going to get used somehow when computing this hash value. But still, if M is like 5, for example, if M is like 7, um, if you expect your distribution of keys to like be non-uniform mod 7, then this is going to be bad, right? Because you're going to end up with a lot of keys hashing to the same place, even though they're different. So you like if you've got like yeah, if you've got some sort of pattern in your input key space, it's very important that a good hashing function sort of tries to destroy that pattern, and that's sort of why like picking something irrational for A helps to do that, right? Because if I multiply this weird irrational number, I mean, I guess it's not that weird. It's like what was this like 1 over the golden ratio or something, right? Um, which is very, very irrational. Okay, so honestly, that's probably why Donald Knuth thinks it's a good number. But yeah, if I multiply a key by some like weird irrational number, then just look at the fractional component, any sort of like keys that are very close together, or keys that like exhibit some kind of pattern, are gonna yes, it is 1/5. Thank you. Um, keys that exhibit some sort of input pattern are not going to that sort of pattern is going to get destroyed when you compute the hash value, right? Um, so that's something that you care about. It is a very crazy number. Um, it's I think this is a bit of a digression, but my favorite, I mean, people maybe already know this, but my favorite fact about phi is that it's like it's the number, it's what you get if you try to make something that's as difficult to approximate by a rational number as possible, because it's like continued fraction is just a bunch of ones, right? So a rational approximation, it's exactly, yeah, it's the most irrational, right? Like a rational approximation is something where the continued fraction cuts off with like an infinity somewhere. And the only way to stop that is to have like a bunch of ones everywhere. And so it's the most irrational. That's cool. That's good. Uh, we like irrational numbers. Um, anyway, yeah. Uh, okay. So does the sort of like this sort of whirlwind of hashing by division and hashing by multiplication. Does that kind of make sense? These are like specific implementations of hash functions. So again, the first thing you have to do is somehow map the data structure that you want to hash into a natural number. And then once you've got a natural number that's maybe unbounded, you apply one of these two hash functions to convert it into something in the range 0 to n. All right, let's talk about collision resolution. I guess said I would talk about earlier. Okay, let's go back to our example of like 1, 3, 2, 3, 5, 6, right? Maybe I want to hash these things mod, let's say mod 4, right? Say m equals 4, which of course we know is bad because m is a power of 2. So let's say m equals 3, right? We've got a table with 3 slots. This one corresponds to 0, this one corresponds to 1, this one corresponds to 2, right? Things start off very easy because I look at 1, it hashes to 1, so I insert it here. I look at 3, it hashes to 0, so I insert it here. I look at 2, it hashes to 2, so I insert it here. I look at 3, it hashes to 0 again. Oh wait, I want to call this a 3. Right? I look at 3, it hashes to 0. I find I already have a 3, so that's fine. I look at 5, this hashes to 2. I try to put it here, but I already have a 2 here, right? So one thing I can do is, instead of calling this a 2, I can think of it as a linked list, right? That just contains a 2, right? So I can replace this with a pointer. I have a 2, and then I'll just add on a 5, right? If I'm making these linked lists, I should make all of them linked lists. This is a linked list that contains 1. This is a linked list that contains 3, right? So I've inserted my 5, which is good. I look at 6, this hashes to 0. So I go back over here. I've already got something. So I just add the 6. I glitched out for a second. Oh no. Yeah, I can go over this again. Maybe I'll just start over. Okay, so Wi-Fi's bad. No worries. Okay, so right, if I've got a table with 3 slots, I'm obviously going to have collisions because I've got numbers from 1 to 6. But one easy way of resolving these collisions is to start by thinking of each of these slots as just a linked list, right? When I insert a 1, I notice that it hashes to 1. So I'm going to insert the 1 into the linked list at slot 1, right? So now I get something like this. I insert the 3 into the linked list at slot 3. So I get something like this. I insert the 2. And now the 3 again, of course, shows up and I already have a 3 here. But the 5 also hashes to 2. But I don't have to worry about the fact that there's already something there because the thing there is a linked list, so I can just add to the linked list, right? And then similarly with the 6, it hashes to 0, but I can just add it to the linked list, right? This is called chaining because we're sort of building up a chain of linked list nodes for each hash table entry, right? So pseudocode here, insert table key. We compute h of the key, or I guess maybe I want to start by saying like init. We create an array of m empty linked lists, right? So now even our hash table, even our empty hash table contains something, but the thing it contains is an empty linked list, right? Insert maybe table key is just table at hash of key dot insert key, right? And this is a linked list insert. Right. And you can replace this linked list with your favorite data structure, right? You can put a doubly linked list here if you want, or a circularly linked list, or a binary tree, or something like that, right? But that's the idea. And then deletion, of course, is the same. We find the key that we want to delete. We figure out which which sort of slot it's going to live in, and then we traverse that particular linked list to delete it, right? Does that make sense? Let's talk about the complexity, right? So um, the complexity of, let's say, or I guess actually, okay, so this is insertion. Lookup is of course the same. If I want to look up a value in the table, I figure out what linked list it's going to be in, and then I traverse the linked list to find it, right? Um, okay, yeah. So basically, all of the operations on this table now include this extra step of traversing over a linked list, but the upshot is I don't have to worry about like two things colliding and like overriding each other. Because when two things collide, I just add the second thing onto the end of the linked list, right? Okay, let's talk about the complexity. Particularly, let's talk about the time complexity. So the time complexity of lookup, right? Um, let's first analyze the case where the key is not in the table. So ignoring complexity for a minute, if the key that I'm looking up is not in the table, what is the sequence of operations that happens? Like what actually happens in my lookup function if I try to look up a key that's not in the table? You can shout it out or put it in the chat. Right. So maybe for example, if I look at this table, right, and I try to do a lookup the key 4, I traverse a whole list. Which list do I traverse? Yeah, exactly. So in particular, I start by I hash the key, traverse the entire list at hash of key, right? Hashing the key is something like theta of 1 if we're using a good hashing function like our multiplication or division based hashing, right? In general, we want computing a hash to be something that looks constant time. Traversing the entire list, what's the complexity of this? Like how many steps is this going to take? Any thoughts? I see n over 3. I see the number of distinct n over m. Yeah, m is the modulus 3. Um, the answer is it depends, right? It depends on what the key was. It depends on what other keys are in the hash table, right? It depends on what our hash function looks like, right? So in general, unless we've fixed like a particular table with a particular set of keys and a particular lookup operation. This is very different, very difficult to sort of analyze. Um, Fortunately, anytime the complexity of something depends on the input, not just on the input size, we can do something like average case analysis, right? So on average, the number of steps is the average length of a list, which, as Aryan and Robert mentioned, is the number of elements in the hash table divided by the size of the hash table, right? This ratio is so important that we're going to call it the load factor, and we're going to give it a symbol alpha, right? So the complexity of looking up a non-existent key is theta of 1 plus alpha, right? Now, if this sort of goes back to one because we've got this hashing step, right? We don't yet know what alpha looks like, so one might be more important, right? Um, but yeah, okay. So if if we make sure that if we know something about what n is going to look like, right? If we know something about how many keys there's going to be, and we make m somehow be proportional to that, right? Like if as the number of keys grows, we also increase the size of the hash table, then we can make sure that alpha is roughly constant, which means that this entire complexity is constant, right? So looking something up is constant time. And you can use the same argument to show that inserting something is constant time, because the traversal you have to do when you insert is the same as the traversal for if the key wasn't there, because you just sort of um, find that find that bucket and then like go through the entire list to insert it at the end, right? Um, and then if the key is there, then it's going to take fewer steps because you're going to stop halfway through the list, and so it's going to be constant time anyway, right? So moral, we want alpha to be theta of 1, right? We want it to be something that looks constant, or something that's not dependent on the input size, right? So we want our table to be uh, in general about big enough to hold the number of keys that we care about, or to hold some fraction of the number of keys that we care about, right? This is collision resolution through chaining. This I think is pretty straightforward. Like I think this is the easiest sort of collision resolution method to understand, um, which is good because the other ones we're going to talk about are a little bit more interesting and often perform better. But before I move on, does chaining make sense to people? Are there any questions? Question, yes. Do we use this for looking things up only? No, right? So you can we have an insert procedure, right? There's a deletion procedure, which again finds the linked list that you care about. and then deletes that key from that linked list, right? We talked about how to delete something from a linked list. So you can insert, you can delete, you can look up. I guess those are the three operations that you can do, right? Is there something else you're interested in doing? It's a more, yeah, it's a more efficient list. It's like a, I mean, it's a hash map, right? So it's something that maps keys to values. Um, and it's the purpose of a hash map is to give you uh constant time access to inserting and looking things up and deleting things. Um, whether you use that to determine whether a value is in a set or whether you use that to like look up a value associated to a key or something like this. Yeah. Okay. If there's no other questions about chaining, I will move on to other collision resolution strategies. I guess one other collision resolution strategy. So I'm going to call open addressing. Okay. So the idea of open addressing comes from the fact that we hate pointers, right? So if I think about how much space I'm using for, let's say, um, let's say the thing I want to store is like 32-bit integers, right? Let's say that's my data type. And say I set m equals 5, right? And I'm storing n equals 10 things, right? How much space does this take up? Well, my hash table has 5 slots, right? Each slot is going to be a 32-bit pointer, right? So maybe I'll just call this like a 4-byte pointer, right? And on top of that, there's 10 linked list nodes sitting somewhere. Each linked list node is going to have um, 4 bytes for the value, and then 4 bytes for next pointer, right? So a table of size 5 holding 10 integers um, is going to take up uh, 20 bytes here plus 80 bytes here, so 100 bytes total, right? If I'm going to be using 100 bytes, I would much rather just set m equals 25, right? So training is great because it means that you don't really have to think very hard about what you do when you insert or delete or look up, right? Because you just kind of ship those operations off to the linked list. The problem is that linked lists are very space inefficient because every linked list node comes with a next pointer. And so the amount of space that you're using for a linked list is like half of it is just pointers to the next node in the linked list, right? If the thing that you're holding is integers, or if the thing that you're holding is like pointer size. And then on top of that, all of the memory that you've allocated for the linked list is outside the table, right? So you're using up all of this space for a table, and then you're also using up a whole bunch of space for linked list nodes. Um, so chaining is conceptually simple, but very memory inefficient, right? The idea of open addressing is, well, so maybe I'll write this. Um, Training is simple to think about, but memory inefficient. Open addressing just makes the table bigger, right? If I'm going to be using 100 bytes, I would rather use those 100 bytes to have a 25 slot table instead of a 5 slot table, and then a whole bunch of like heap memory for linked lists, and then like a whole bunch of pointers to manage, a whole bunch of like dereferences to do, um, cache misses, all of this other nonsense, right? Um, of course, making the table bigger doesn't mean that we're not going to have collisions, because I still might have like more keys and then have them hashed to the same spot, right? So, um, but the idea of open addressing is when there's a collision in a particular hash slot, we just put the key in a different slot instead, right? So here, when there's a collision, put the second key in a different spot in the table, right? So in order to understand this, I'm going to think of my hash function. Instead of going from a set of keys, the range 0 to m, I'm going to think of it as going from a set of keys and a number 0 to m to 0 to m. Maybe I'll call this like h tilde, right? And I can define this as like h tilde k comma 0 is just the ordinary h of k, right? But now I need to think about what happens when I increment this, right? So if I start by assuming that I have a function like this defined, I can rewrite my insertion procedure, right? So initializing is just allocating a bunch of space for this table, and I don't have to like initialize anything in there because it's not going to be linked lists or anything. It's just going to be like garbage values or zeros or whatever. To insert, let's say table comma key. I start by saying maybe let I equal 0, and then I say h equals k comma I. If actually, I think I want to say while table at h is not empty, I equals I plus 1, increment. And then finally, I found something. Uh, I found an empty slot, and I can just insert to that slot, right? Table at h equals e, right? Of course, there's a thing I'm missing here, which is if I run out of slots, if I equals m, throw an error, right? Because this means that the table is full. Does this procedure conceptually make sense? There's a hidden assumption that I'm making here. I'm going to ask you what that is in just a moment. But does this idea make sense? So I have, instead of a single hash function, I have a family of hash functions. Um, and uh, every time I hash something, If there's already a key hash to that spot, then I just increment I and I move on to the next spot and the next spot and the next spot and so on until I find something that's empty, right? Um, and then lookup is sort of similar, right? In that I start I equals 0, I hash the key with I, and then while the table at hash does not equal the key, um, if table at hash is empty, return not found. Otherwise, I increment I and I compute the new hash, right? And then finally, I return, once I found something, I return. And again, I forgot if I equals M, return not found, right? So the idea here is we start somewhere and then we just kind of like if there's already something there, we probe the next position. If there's something there, we probe the next position and just keep going until we find an empty spot to put the key. And then because the sequence of things that we probe is fixed, um, when we look something up, we just sort of keep probing until we find the key that we care about. And if we ever hit an empty spot, then we know that there isn't we know that the key doesn't exist in the table, right? Um, has anyone spotted what's wrong with this, or like I'm what I'm assuming that I haven't said out loud, or like what extra assumption I need for this to actually work? What happens if well, okay, actually, I guess maybe uh let's vote on this first. Um, do people think that there's nothing wrong with this? Like, do people think that this will work um and only throw an error if the table is full? What happens if let's say you throw an error if a lot of things have the same h of k? So if a lot of things have the same hash, if a lot of different keys have the same hash, ideally, the first one goes in the right spot. The second one goes to the next probe position, right? Uh, the third one finds the like position 0, fails, goes to position 1, fails, moves on to position 2, and then sort of keeps going until the table is full. That's the idea, right? If I've got more than m things that I mean, if I've got more than m things that I'm inserting into my table, I can't do anything about that, right? The table's full. Um, but otherwise, uh, like is the if I've got fewer than m things, even if they all hash to the same thing, in theory, this should let me put them all into the same table, just at different spots, not at the same position, right? But what happens if, let's say, we've got um, m equals 4, and I want to insert 1, 3, 5, 7. That good? Yeah. I'm gonna insert 1, 3, 5, 7, right? Four keys, four slots. This should be fine. I should be able to put them all into the table, right? H of K is just K mod 4. Nice and easy. And then actually what I want to say is H of K comma I is K plus 2I mod 4, right? So when I equals 0, I'm just looking at K mod 4. When I equals 1, I do K plus 2, and so on, right? What happens if I insert these four things into a table? All right, 0, 1, 2, 3. I go to insert 1, right? What slot does 1 go into? 1 goes into 1. I go to insert 3. Where does 3 go? 3 goes to H of 3 comma 0, which is 3 plus 0 mod 4, which is 3 mod 4, which is 3. So 3 goes to 3, right? I go to insert 5. 5 wants to map to 1 because 5 mod 4 is 1, or 5 plus 0 mod 4 is 1. There's a collision there, so I increment I and I try again. So instead of 5, I look at 7. 7 mod 4 is 3. So I try to put it into slot 3 instead. But slot 3 is already full. So increment I again. I is now 3. So do 5 plus 6 is 11. Mod 4 is, did I do that wrong? 5 plus 4 is 9. Mod 4 is 1. So try to put it into 1. That's full, so I increment I again. Um, now I is 3, so I do 5 plus 6. Mod 4 is 3. I try to put it there. That fails. And so now I has maxed out. And I say, okay, I've checked every possible slot of the table. The table's full, I can't insert it. But obviously, the table is not full. We've got space here, and we've got space here, right? So the thing that has to be true, essentially, is for this function, k cross 0m to 0m, restricting to a particular key. If you think of this as a function from probe index to probe slots, this should be surjective, right? In other words, for any given key, the probe sequence should visit every possible element, every possible like value, or every possible slot in the table, right? So a better probe sequence here would be something like h k comma I equals, let's say k plus 3i mod 4, right? Now, if I try to insert, if I insert 1, it goes into 1, right? If I insert 3, it goes into 3. If I try to insert 5, what happens? Where does 5 want to go? The first place I want to insert 5 is h of 5 comma 0, right? H of 5 comma 0 is 5 plus 3 times 0 mod 4, which is 5 mod 4, which is 1. So 5 wants to go here. That doesn't work. So I increment I, and I instead try to put it in 5 comma 1, or in h of 5 comma 1. which is 5 plus 3, which is 8. Mod 4 is 0. So I can put 5 right there, right? Same thing with 7. That's a 7, right? 7 wants to go into h of 7 comma 0, which is 7 mod 4, which is 3. So try to put it into there. That doesn't work because there's already something there. So instead, I increment I, right? And I get 7 plus 3 is 10. Mod 4 is 2. 2 is empty. So I put it there, right? Now, if I'm searching for 5, if I want to look up 5, right? I can do the same thing. I hash 5 comma 0. Remember, if I'm looking up 5, I don't know how many times I had to probe to find the 5, right? So I have to start by hashing at 5 comma 0. I look here, there's something here, but it's not the thing that I want. Okay, so I'm going to increment my I'm going to increment I, right? I increment I hash 5 comma 1, and I find it right here, right? If let's say let's do let's say I wanted to insert let's say this 10. Yeah. Let's say I didn't insert the 7, right? And I want to look up 10, right? 10 starts at 10 mod 4 is 2. Oh, and I immediately know it's not there, right? If I wanted to look up 11, 11 mod 4 is 3. I look there. It's not the thing that I care about. So, right, I hash 11 comma 0 equals 3. Table at 3 is not what I care about. So I hash 11 at I equals 1, which is going to be 14. 14 mod 4 is 2. I go to here and I see that 2 is empty. And so I know that 11 is not in the table, right? Because if it were, then I would have put something into the slot already. Like if it were, it would exist in this slot, or if it were in a different slot, that would be only because something has already showed up here, right? Um, it is 9:45, so I'm going to let you go after I define this. This is called linear probing, where h of k comma I equals k plus a times I mod m. Okay, that's all I got. No attendance poll. All right, I'll stick around if there's questions. Um, but on Monday we'll talk about uh, quadratic probing and double hashing. If you still need to do yesterday's, you still have like a couple hours. But yeah, you are free to go. I'm gonna stop the recording.